Dear children, let's move on to do lesson number 4 now. In the previous 3 lessons, we talked about electrostatics and also current electricity. When you have an electric charge, it's going to create a field around itself, the electric field. And if you bring a second charge in that field, and the second charge is going to be affected by the first charge, and the first charge is going to be affected by the second charge. You can choose to study what happens to each charge. These charges will experience a force. And if you don't allow the charges to move from their position, either by nailing the charges or by holding the charges in your hand or by any other unspecified force, then the study of this scenario is called as the electrostatics. And after this, we talked about current electricity. In this case, we allow the charges to move. In electrostatics, the charges are stationary. They just move very quickly and then settle at a position. But if you allow them to continuously move, then it is current electricity. And that can happen if you maintain a potential difference between 2 points or 2 ends of a conductor. Then a current will flow from one end of the conductor to the other end. But what happens when charges flow, when charges move from one position to another? They constitute a current, and they also result in another phenomenon. It's called as magnetism. Moving charges create magnetic fields. Charges, whether they are stationary or moving, will have an electric field. But if they move additionally, then they will also produce a magnetic field. Even though electricity and magnetism had been known to people for a very long time, for thousands of years, more than 2000 years, people thought that they were two different phenomena. But in 1820, exactly 200 years ago, a Danish physicist cum chemist, Hans Christian Ørsted, demonstrated that moving charges and electric current can produce a magnetic field. Like any other discovery, this was also accidental. He was in his lab, and there was current flowing through a wire, and there happened to be a magnetic compass by the side of this wire. So it started deflecting. As he increased the current in the wire, the deflection in the compass was more. Or if he kept the current constant in the wire, if he brought this compass nearer, then the deflections were more. By moving the compass to different places, he found something else too. He found that what you can call as the magnetic field lines, they were circles around this wire in the vertical plane. So if this is a wire, then magnetic fields formed concentric circles around this wire. This wire was the center. He established that in 1820. And all the development in electricity and magnetism has taken place only in the last 200 years. In fact, magnetism, the word itself, comes from the Greek word magnesia. Magnesia was a place where Greeks first noticed lodestones. Lodestones are the magnets that you use on your fridge. They're magnetite materials. Actually, the name is Magnetis lithos. What does lithos, means stone. Magnetis lithos, the stone from magnesia. That was a name given to it. And later it went to Latin as magnetum, and when it came to English it became magnet. So a moving charge will produce a magnetic field. A charge, she said, whether it is moving or not, will always have an electric field associated with it. But if it is also moving, then it will produce, in addition to this electric field, a magnetic field too. Now we know that without current, there can be no magnetism. Even the lodestones have this magnetism because of the atomic current. You have electrons revolving around the nucleus. So electron is a charge, and if it moves around the nucleus, then it's a moving charge. Moving charge is current. And if there is current, we just said that there would be magnetism. So the lodestone that you see has its magnetism because electrons are revolving around the nucleus inside the lodestone. Then you may ask this question: every atom has electrons, then why are some materials magnetic and some other materials are not magnetic? Now that is because each electron will produce its own magnetic field. And the electrons will have to be in a certain alignment for you to produce a net magnetic field. Otherwise, a magnetic field produced by one electron can be cancelled by the magnetic field produced by one or more electrons. So, this is the reason why some materials have magnetism and some other materials. So, in the year 1820, the Danish physicist Hans Christian Ørsted proved beyond doubt that current produces magnetism. Current is nothing but moving charges, so moving charges produce magnetism. And this magnetism is a function of the position vector. So what do we mean by that? What I mean by that is, suppose this is a wire through which the current is flowing, and if I measure the magnetic field produced by this current, the moving charges, then I will have some value here. And if you measure the magnetic field here, it will have a different value. And here, it's another value. And there, it's another value. Here, another value. So this magnetic field produced by this current is a function of the position vector R, where you measure it from the wire. So B is a symbol you use for magnetic field, and this is a function of R, where R is a position vector. This leads us to a set of questions, but the first of them would be this. Let's take an electric charge. and that produces an electric field around it. And if I take an electric charge that produces an electric field around it and keep it in the presence of an external electric field, then this charge experiences a force. We know that. Coulomb gave us the equation for that. Likewise, let us take this moving charge. The moving charge produces a magnetic field around it. So if I place this moving charge in the presence of an external magnetic field, I am placing this moving charge that produces its own magnetic field in the presence of an external magnetic field. Now, will it experience a force? It turns out that it does. And the force experienced by this charge is given by this equation. Force, I call this as a magnetic force, experienced by a charge Q. I can consider that to be positive now, which is moving with a velocity v in the magnetic field B is given by the vector cross product of V cross B, QV cross B. So what it means is that if B is a direction at this point of the magnetic field, and let's say this is the velocity of the charge Q. If they are separated by an angle theta, these two vectors, then the force will be in the direction given by the cross product of V and B. So it's going to be V cross B. So V cross B. So this would be the vector. So this vector will be perpendicular to both V and B. So the magnitude can be written as Q V B sine theta, and then the normal vector. So that would be your F. So this tells you this is the normal vector in the perpendicular direction. So Q V B sine theta is the magnitude of the vector. So Q V cross B. That's the force experienced by a moving charge Q with velocity V in an external magnetic field. See, this B is not this B. When I talked about this, I said this is a magnetic field produced by the charge, but this B is different from that B. This is an external magnetic field. Okay, so I call this external magnetic field. Okay, suppose I have a moving charge. With this charge Q, and let's say this is moving in this direction. Suppose I bring both a magnet and also another charge which will produce an electric field near this. And let's see what will happen. I bring a magnet, let's say this is a ball magnet, let's say this is not, and here's some sound. So this will set up a magnetic field there. And another charge Q. So this magnet will have its own magnetic field, and this Q will have an electric field here. So this point, at this point, you will have a magnetic field due to this and also an electric field due to this charge. Now, what will happen to this? The charge Q, small q, which is moving with a velocity v. Well, it's going to experience force due to both of them. There will be an electrostatic force due to Q, and there is a magnetic force due to this magnet, because this is a moving charge. This charge is not stationary. If the charge is stationary, it won't be affected by this. It will be affected only by the electric charge. You can look at that from the equation. If V is 0, then there is no force. So if stationary charges will not be affected by the magnetic field, but moving charges will be affected by the magnetic field. And whether the charge is stationary or moving, it will be affected by the electric field produced by this. So the net force experienced by this will be force due to the electric field of Q plus force due to the magnetic field of this magnet. So what is the force due to the electric field? Q is a charge, and let's say like E is the electric field due to this charge. So this would experience QE. Maybe something like this. E is in this direction. And north. So B will be in this direction. And what about the magnetic force? So that is given by this equation, which is Q V cross B. So this equation is called as the Lorentz equation or Lorentz force. This is called as the Lorentz force because H.A. Lorentz was a person who synthesized this based on many experiments done by Ampere and others. So this equation is called as the Lorentz force equation. So the total force experienced by this would be the sum of the force due to the electric field and the force due to the magnetic field. So if I take this one, the force could be acting, electric Fe could be acting like this, and V cross B, then it will go somewhere like this, that will be FB, and the net force will be the sum of these two. Hope this is clear to you. Okay, so let me take this idea of a moving charge experiencing a force in the presence of an external magnetic field little further. I am going to consider a conductor where current flows, and I am going to keep this conductor in an external magnetic field. Now this conductor must experience a force. Why? Because there are free electrons which are moving in the conductor. And those electrons, since they are moving in the presence of an external magnetic field, will be experiencing a force. And ultimately, that force will be on the conductor. The force experienced by the free electrons of the conductor will be the force experienced by the conductor itself. So let's see how to do this. Let me consider a conductor. Okay, current I flows through this. This conductor has a cross-sectional area of A and length L. So the current in the conductor happens because the free electrons in the conductor move. Let N be the number of free electrons per unit volume. A number of free electrons per unit volume. We know that it's going to be different for different materials. If you take aluminum, you will have one value. If you take copper, you will have a different value. So you are going to find this N. N is the number of free electrons per unit volume. Okay, what should I do now? I need to find the number of free electrons in this entire conductor. Because if I keep this conductor in the magnetic field, and if these free electrons are moving in this direction, then they will experience a force. So I need to find the total number of free electrons in this conductor. So that would be, if N is the number of free electrons per unit volume, then the number of free electrons N, capital N, is equal to N into volume of the conductor. What's the volume of the conductor now? A is the cross-sectional area and L is the length of the conductor. So I'll say N to AL. So that's the total number of free electrons. So all these electrons will be moving in this direction. What will be the velocity of those electrons? Well, this will be the drift velocity. We have already come across this. When current flows through the conductor, then the electrons drift with a certain velocity. So that is the effective velocity in the direction. So the velocity V is actually the drift velocity. So now, can I calculate the force acting on this conductor? Let B be the magnetic field. The magnetic field must be at an angle to the direction of the charges. Because if B is in the same direction as the velocity of the charges, no force will be experienced, because the force experienced is given by the equation Q V cross B. So you need to have an angle between them. If they are parallel, then this term will become zero. There will be no force experienced by these charges. So I am going to make use of this equation. So B is acting, let's say it's perpendicular direction to the direction of the flow of electrons. So now, what is my Q? My Q is the charge on each electron and the total number of electrons that are moving. That's the total charge. So what would I get here? So that would be N into Q. Q being the charge on each electron, or I can put E. So that becomes my Q. And then velocity cross B. So what is this? N is actually small n into AL. Small n, AL, and then E, and V is actually VD. Cross B. So you may remember from your previous lessons that V, E, N, A is actually the current. I is equal to V0. So this will be I. But the current is not a vector quantity, so I cannot associate the vector to this current I. So I won't associate it to the length L. I'll take the direction of L to be in the direction of flow of the current. This current is not a vector quantity, so I'm going to associate this vector to the length. So it's going to be I L cross B. So the force experienced by conductor will be this. So I L cross B. Okay? Note that if the electrons are moving in this direction, then the current will be moving in this direction. Okay? That is automatically taken care of. Let me tell you like how. Because note here, I have assumed the current to be flowing in this direction, which means that the electrons must be moving in this direction. So my Vd is in this direction. Okay? Vd is in this direction, but what will happen to my E? E will become negative. So Vd cross B will give me, and if suppose B is in this direction, and electrons are moving in this direction, because current I am considering it to be moving in the direction. So this is V, and then B is like that. V cross B is actually down, but that is only for positive charges. But because I have electrons which are negative charges, E will be a negative quantity, so this force will be up. So this conductor should experience a force up. Understand this clearly. Current is in this direction, which means electrons are moving in this direction. So V is in this direction. Let's say B is in this direction. B goes through the board. So V cross B V cross B is down. But that is for positive charges. Q is positive, then that's what we'll get. But electrons are negative. So what will happen here is, it will go up, because like you will have a negative here. Instead of Q, you will have, instead of E, you will have minus E there. So the force will be like that. The force acting on the conductor is upwards. Let's see if that works here. I is in this direction. He said B is in this direction. I is in this direction. So IL is in this direction. Okay? IL cross B up. So it matches perfectly. Let's do the example problem 4.1. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 amperes. It is suspended in midair by a uniform horizontal magnetic field B. What is the magnitude of the magnetic field? Okay, you have a conductor, and through the conductor a current of 2 ampere is flowing, and no other information is given. This is my imagination. So there is a conductor in midair, maybe there is a battery here, and then there are wires which is just touching the conductor and sending a current through the conductor. If there is nothing else, then this conductor will fall, because the conductor is just touching the wires. So that is how I imagined. So this will fall. But now it is not falling. If it is not falling, then there must be another force acting on it, upwards. Gravity is acting down, and this force must be acting up to balance this. Then what is that force? And that force is the magnetic force acting on this conductor. You see, this conductor is kept in a magnetic field, an external magnetic field. So the direction of the magnetic field is into the board. Why do I say that? Look at this symbol. This cross symbol tells you that the field is into the board. I need to explain this a little. So far, you did not need any symbols like this. And why do you need the symbols like this now? Previously, if there were two vectors, you are adding or subtracting them on the same plane. If you have V, if you have B, if you add these two vectors, then V plus B will just add, or A plus B will just add on the same plane. But now you are going for a cross product. You have V, you have B, then V cross B will give you a third vector which is 90 degrees, which is perpendicular to both these vectors. Now it is no longer a plane, now you are talking about a three-dimensional space. So we don't have three dimensions here, we only have 2 dimensions. Then how do you represent three-dimensionality in 2 dimensions? And that is why you use these symbols. You say that the vector is going into the board. It is like an arrow. What you are looking at is the tail of the arrow. The tail of the arrow will be like this. The arrow will be something like this, right? This is your arrow. And there would be a okay. So this then there will be other 2 plates like they will be kept, perpendicular to this. And if you were to look at this arrow from behind, then the tail will look like this, or plus, or cross, however you want to say. But if you were to look at it from here, then it will look like this. So when I see this symbol, I know that it's coming towards me. This is the tip of the arrow, and that's the arrow here. So the arrow is coming towards me. When I see this symbol, I know that the arrow is leaving me. It's going into the board. This is coming out of the board, and that is going into the board. So those are the symbols we'll be using. So here I have B with this symbol, which means that the arrow is going into the board. The field is in the direction. The magnetic field, the external magnetic field, is in this direction. Current is in this direction. So, what is the force experienced by the conductor? It's going to be IL cross B. So IL is in this direction, B is in this direction. So IL cross B, then I'll get an upward force. So that upward force sin theta would be sin 90, so that becomes 1, because I is here, B is here, so the angle between those two vectors is 90 degrees. So I just get ILB, sin theta value will be 1. So that's magnitude. So this force, if this force balances this mg, then this conductor will be suspended in air, it won't fall. So this magnetic force Fm must be equal to force due to gravity. Then there will be no net force on this conductor. So the conductor will be stationary here. Even though the wires are just touching, now it won't fall. Because there is this force due to the magnetic field which is acting upwards and is now balancing the gravitational force. So this is ILB equal to Fg will be mg. I need to find B, so B is equal to mg by IL. So what is B here? Is equal to what is M? M is 200 grams, which is 0.2 kg. 0.2 kg. And that would be, I'll take 10. So 9.8. I'll take 10 meters per second square. Divided by I would be 2 amperes now. 2 amperes. And L is 1.5 meters. So if I come to this, then this will 0.2 into 10, 2 will cancel. So I'll have 1 by 1.5, and then all these quantities, all these units will be present, and I would call these units collectively as Tesla, because Tesla is a unit for the magnetic field. So this is Tesla, T, Tesla. So this would be 1 by 1.5, 1.5 is 3 by 2, so 2 will come up, and so 2 by 3 is equal to 0.66 Tesla, roughly, approximately. Because I am not using 9.8, I am using 10 here, so this is going to be an approximate value. Okay, so B is approximately equal to this. And Tesla is a unit for B. Hope this is clear to you. Now let's do example problem 4.2. So what does it say? If the magnetic field is parallel to the positive y-axis, which way would the Lorentz force be for A, electron, B, proton? So we need to go with the picture. So X is in this direction, and Y is in this direction, and Z is in this direction. So X cross Y gives you Z. So I have told you already that we must be using the right hand coordinate system. So this is X and this is Y and this would be Z in that case. Okay. And it is said, and look at these crosses. They tell you which direction the magnetic field is. The magnetic field is going into the page now, into the board. It's parallel, B is parallel to the positive y axis. The positive y is there, so B is in this direction. What is this V? V is the velocity of both the proton and the electron. They both move along the positive x axis. So now you need to find the direction of the Lorentz force, magnetic force, okay, experienced by these two things. First, for electron, what is the force experienced by the electron? Okay, F is equal to Q to V cross B. V is in this direction, B is in this direction, so V cross B will give me the upward direction. So V cross B is upward. But what about Q? For electron, Q is negative E, minus E. Minus E into V cross B. So V cross B will give me an upward direction. Because I have minus E, then that will become downward, because it's going to be in the opposite direction. So the force acting on the electron will be downwards. V cross B gives you upward direction, but electron is a negative charge, so minus E, that gives you the downward direction. So the force experienced by the electron will be in the downward direction. So this is the force experienced by the electron, and that is along the negative Z direction. Now this is Z and this must be negative Z. What about proton? F again is equal to Q to V cross B. So Q for proton is simply E, or positive E, and this will be V cross B. So V cross B, as we just saw, is upwards, and this is positive, so there is no change in the direction. So the force, the Lorentz force acting on the proton would be upwards. Proton. So that would be in the positive Z direction. Hope this is clear to you.